So let's get started right at it. The purpose of this worksheet is to introduce you to some equilibrium problems with acid and base principles. So let's get right at it. A silly student prepared a 0.10 molar solution of formic acid and measured the pH of the solution to be 2.38. Now we know that the pH, okay, represents the negative log of the H plus or the hydronium H3O plus concentration. That's water holding on to a proton. So that's the link to this question. The link is they're giving me the pH. Now let's understand what's happening here. So what we have here is we have formic acid and we have H. Notice the H in front signifying that it likes to give that off. HCHO in equilibrium, because now it's a weak acid, so it's not just going forward, with, let's say, H plus. Now we could put H3O plus there, it's synonymous, plus what's left over after this donates a proton, which would be the conjugate base. Notice if you lose an H plus, now the CHO is going to be negative. All right, so again, some basics here. This is the conjugate acid. This is its conjugate base. And what we learned in class today is there's a push and pull with this reaction, meaning there's the Ka, or the ability for it to react this way, and then there's a Kb, ability to go in the reverse. To act as a base, it would accept this proton back, and since it's a weak acid, that means it doesn't like to go forward all the way. So the question is, what is the equilibrium, or this question is, what is the Ka for the forward direction? Now the Ka, remember, represents some position. Now Ka is a fancy word for the acid dissociation constant. It's nothing more than an equilibrium constant for this reaction. We have our reactants, which is the acid, and we have the products, which are the conjugate base and the proton. The question is, where is this position? Does it favor the reactants and products? And I want you to think, to understand this. There's a battle for the forward reaction, which would be the Ka reaction, is a battle for the reverse. Who is winning? Okay, and the idea here is this conjugate base and this acid don't really interfere because they're parts of two separate reactions battling for supremacy, so to speak. In any case, we're going to call it Ka, but that's what we're about. How well does the forward reaction go, which would be the Kb, as compared to the Ka? All right, as we learned today, the Ka times the Kb is Kw, so it's an inverse type of relationship. Meaning, if the forward reaction is really good, that means the reverse reaction isn't very spontaneous. And if the reverse reaction is really spontaneous, that means the forward isn't. That's what we're after. Okay, so back to the problem and less of the theory. The pH is important. So they gave me a pH to be 2.38. Now, why'd they give this to me? Well, think about what we have here in a nice table. We have I, C, and E. We have initially, and now initially I have 0.10. So I'm going to write that in, 0.10 molar. And I can for this because this would be an aqueous, as all of these are also. And you can assume that to be true. And we're going to assume before it breaks apart into these ions, we have none of these. Okay. And then, of course, as it goes forward, we're always going to assume these equilibrium tables as we're starting right here. The Q is tremendously small compared to the K. So we're always going to start in that theoretical position. So this is going to be minus something because you're going to lose some proton. And this is going to be plus that something and plus that other something. Notice they're the same X because for every one H plus loss, there's one conjugate base. All right. And then at equilibrium, this is going to be 0.10 minus x, and this, of course, 0 plus x is just x. Now, they want us to solve for the Ka. Okay, well, if you think what the Ka really is, the Ka, okay, is equal to the products, which in this case is the concentration of the H plus over the reactants. Now we got the H plus and the conjugate base over the reactants, which is HCHO, concentration. These are all aqueous solutions. Notice there's no 2's or 1's, so the coefficients are 1. So products over reactants, coefficients become exponents, and solids and liquids do not apply. So to solve for the Ka, we're going to need some values. Okay, well, I got to solve for this. This is 0.1x. I don't know Ka. I do know that the concentration of my of my acid is this, so that potentially go there, but I have 1, 2, 3 variables. So the pH is the key. And what do we know? I can convert this pH into the actual concentration of the H+. So how do we do that? Well, if you remember, to go from the log to the actual number, it's 10 to the negative, whatever the pH is. So in this case, it's 10 to the negative 2.38. So do second function, find the 10 to the x button, and then go negative 2.38, and that's going to make back the regular number. And when you do that, the concentration of H plus with this pH is 4.16 times 10 to the negative 3. That's the concentration of the H plus. And of course, that would have to be at equilibrium. Okay, they don't say saturated here like a KSP problem, but it has to be at equilibrium. Okay, and so, well, gosh darn it, that's the value of H plus at equilibrium. So my X, all this plus Xing and stuff, is this 4.16 times 10 to the negative 3. And so this is the same value because it's a one-to-one relationship. Yes, sirree Bob. And so all we're going to do is put these values here, put this value here, and our only problem we have is this 0.10 business minus x. It's not a problem because, party people, compared to this small x, this is a weak acid. Weak acids barely dissociate. So we can assume that the x coming off is so small, it's small compared to this value. So this x is actually 4.6 times 10 to the negative 3. So if you notice, that's 0.004. That's insignificant compared to 0.1. So that's our x. So you could subtract it if you like, but we can approximate it away. So the value of x is that number, and this number is so much smaller than that, we can just approximate it away, and then when we do the work, what we get is 4.16 times 10 to the negative 3. Now you can write that over again for the conjugate base, but we know that's going to be squared, okay? All over 0.10 minus that number, but that's so small compared to it, it won't significantly change your answer, okay? And we're going to solve for KSP. I mean, Ka. Gosh darn it, can't get out of my mind. So Ka. All right. So when I do that work, I get my Ka to equal 1.7 times 10 to the negative 4. And of course, that's a small number. Why is it a small number? Weak acids barely dissociate. All right. The second part of this is what's the percent? So the answer here is 1.7. Now, if I'm checking my sig figs, just making sure I'm accurate here, 2.38 is 3. 0.10 leading zeros are not significant, so I'm rounding to 2 sig figs, and I believe 1.7 does that. So 1.7 times 10 to the negative 4. All right, because you can see the extra little piece of acid base that, you know, gives some complexity here. We had to take this pH, make it into a concentration, and then use it in our ice table. Now, did we need our ice table really? But it helps to see what's going on. Definitely, as we continue down more advanced problems, the ice table is going to help you think your way through these. Okay, now 2, what's the percent of the acid ionized? What does that mean? Well, if I have an acid called HA, and it barely ionizes, what that means is very few of the HA molecules will break apart into H plus and A negative. That means that most of the beaker that has a solution is going to be made of undissociated, kept together HA molecules, and very little will be the conjugate base and the proton. Okay, weak acids barely dissociate, but we want to know the percent ionization. So how do we do that? Well, we know exactly how much ionized. There, right there. This is telling me exactly what's the ratio. Look at the stoichiometry. For every what? One of these, there is one of these, okay? So I know exactly how much I started with, 0.10. So I'm going to put that as my total. That's the total I start with, 0.10. Remember, percentages are what? Part over total times 100. So that's what I'm starting with. And how much did it ionize? Not much, okay? And that answer is 4.16 times 10 to the negative 3. Okay, divide that number by 0.1, and then times it by 100, and you can see what you're going to get very simply is 4.16, okay? And that'd be percent ionization, okay? Now, just a quick little fact that you can bring to your lunchroom table. You're allowed to approximate this away if the value of x you're approximating is less than 5%. So we actually just proved that x we subtracted was less than 5%. So you'll never have a scenario where you have to, but it's just a fun fact to share with your family and friends. Okay, so this is a little bit of review here. Okay, and what we have here is two weak acids and bases. They're both amphoteric. And why are they amphoteric? Well, this being negative means that it could absorb a proton and become what? H2SO3. But because it has an H, it can also give off a proton to become SO3 negative 2. Same thing happened here. Because it's negative, it can accept a proton and become H3PO4, or it can give off an H for the same reason. So the question is, just by looking at this alone, I can't figure this out. So what we're going to need to do is go to some kind of table and read what the Kas are for these acids. So I'm going to go to my the table L that I gave you for acids. So let's go find HSO3 ion. Let's go find its Ka, its ability to dissociate, act as a good acid. All right, so I'm going to list of charts that give me Ka, strengths of acids, and I'm looking for HSO3 negative, and there I found it right in the middle here, and its Ka is 1.1 times 10 to the negative 7, okay, and the other one I'm looking for is H2PO4, which is 6.2 times 10 negative 8. Which number is bigger? Clearly HSO3 negative is bigger. Now what does that mean? They're both very tiny, and that means that the products, which are the ions, don't really dissociate very well, but this one dissociates a little bit better with a bigger Ka, which means more products, which are more ions, which means you're better at losing the proton than this one. This one is going to act as the acid. So because of the higher Ka, this is the acid. They both can act as an acid or base, as I just described, but this one is better at being an acid. So knowing that, that's my acid, it's going to make a conjugate base. Now conjugate means the same chemical plus or minus an H. So if this is an acid, it's going to, like a Bronson-Lowry acid, it's going to donate an H plus. Okay, and what's remaining is its conjugate base, SO3. Now it lost an H plus, so now it was negative 1, so this is negative 2. This gained, now this of course is its conjugate base, and now this chemical is acting as a Bronson-Lowry base because it's accepting a proton, and it's gaining an H plus, so now it's H3PO4. All right, now it has no charge because it was negative 1, and adding an H plus to the mix makes it neutral. And this, of course, if this is the base, its conjugate pair must be its conjugate acid. Okay, and there it goes. So list the two Bronson-Lowry bases, H2PO4 negative. Who's the other base? That would be SO3 negative 2. Who are the acids? That's HSO3 negative and H3PO4. So make sure you understand the conjugate pairs are the same chemicals plus or minus an H. All right, you can't have a conjugate pair. All right, so if we look at one conjugate pair, it'd be the H2PO4 negative and the H3PO4. Now they said, I guess, conjugate acid-base pair. So this is my acid, and this, of course, my base. I guess I should have wrote that opposite, but hey, I'm tall. what's the conjugate acid of HCO3? So when it is the acid form of this, so this is the base. So what did it look like to become this base? It must have had one other proton. So the conjugate acid is HSO3 negative 2. Negative 1 because you just added a proton. So this would be HSO3 and now negative 1. Okay? Just like if I said to you, what's the conjugate base, okay, of, let's say, NH4 plus. So if you're looking for a conjugate base, this must be the conjugate acid I gave you, and to be a conjugate base, you must have did what? Okay, you must have less or acted as an acid and gave up your proton to become the base form, which has an opening, which is that lone pair, NH3. So the conjugate base always has one less H than the conjugate acid. So if I want the conjugate acid of something, it's going to have one more proton. Okay, pretty simple. So now calculate the Kb for the acid in the forward direction. So the acid in the forward direction was HSO3 negative, and its Ka, let's go get it again because my short-term memory is gone. 1.1 times 10 to the negative 7. So it's 1.1 times 10 to the negative 7. And it has no units because it's an equilibrium. Equilibrium is a dimensionless value. But now I want the Kb, which, what does that represent? That represents the reaction in the reverse. How well does this base go in the reverse, in the battle of equilibrium between the acid and the base? Okay, well, we learned today that Ka times Kb equals Kw. I did that little proof for you. So I have the Ka, which is 1.1 times 10 to the negative 7. And I'm going to solve for Kb, so it's going to equal Kb. And I'm essentially, hold on, let me get in too fast here. I know that the Kb is what I am solving for. So this is times Kb. And we know the Kw is 10 to the negative 14. So to solve for Kb, Kb is going to equal 10 to the negative 14 over 1.1 times 10 to the negative 7. And when we do that craziness, we get a Kb that's equal to 9.1 times 10 to the negative 8. All right, and so you can see it's a little bit better at being an acid, it's a little higher than being a base. All right, so it's kind of almost kind of in the middle somewhere. It's terrible at being an acid and also terrible being a base, but it still shows you the ability somewhere is this is not that better by much being an acid. Okay, but in any case, the answer is 9.1 times 10 to the negative 8, and that's equal to the Kb. So moving on. Okay. Okay, so here's another question I want to go over with you. And here we go. What is the hydroxide ion concentration of an aqueous solution that has a hydronium ion concentration of 8.2 times 10 negative 3? So they gave me the hydronium. Sounds similar, but it's H3O plus. And they gave me the H3O plus concentration to equal 8.2 times 10 to the negative 3. All right, so a couple ways I can do this. I know that the concentration of the H3O plus times the concentration of the hydroxide must equal Kw. So we could put this in here, and then I could also do what? Solve for it. I'm a big fan of finding the pH, but again, it's probably easy to do that. So we go 10 to the negative 14 divided by 8.2 times 10 to the negative 3. All right. And so when you do that math, okay, I put that in my handy dandy calculator, I get my hydroxide concentration to be 1.2 times 10 to the negative 12. Pretty simple. 1.2 times 10 to the negative 12. There's no equilibrium here because I'm giving you the hydronium concentration. And really hint here, if they were giving you a strong acid, they're really giving you the concentration of the H plus or the H3O plus if it was a strong acid. There's no equilibrium if you know this concentration. What's the pH? Okay, well, very simply, I can take the negative log of the 8.2 times 10 to the negative 3. That's kind of easy stuff, isn't it? And when I do the negative log of that, I get 2.086, okay, which that means the pH is equal to, I'm going to go with 2 sig figs here, so 2.1. Okay, pretty easy. There was no equilibrium in that question. Now, number 10, they want the pOH of a solution that's 0.150 molar HF. Now, HF is a weak acid, okay? And they may even tell you that, but we can look on our chart right now to know it's HF's a weak acid. So HF comes across here to make H plus and F negative. Now they want the pOH, so we want the value of X. So right now I have 0.50. I have 0 initially. Here's my ICE table. Pretty easy. It's going to be minus X, where I was going to start with 100% of this. This is going to be plus X and plus X. Easy steezy. Okay? At equilibrium, it's 0.50 minus X. You probably can know what we're going to do with that. And of course, this is X and X. Now, to know this concentration, I'm going to have to know something about HF. So I'm going to need to look up, all right, it's Ka. The Ka of HF is equal to the what? The concentration of H plus to its power times the concentration of F to its power, which is 1, over HF, which was aqueous. All right. So we know, if we know what the Ka is, we can do this. So if I look up my Ka from my table, I find the Ka to be 3.5 times 10 to the negative 4. And what's that going to equal? Well, this is X in X. And this we're going to approximate away because it barely goes forward. So we're going to have X squared over 0.5. And when we solve for X, you're going to times that by 0.5. Okay. And then you're going to do the square root of both sides. Okay. You get an X that equals, and then you can try this out yourself, 1.32 times 10 to the negative 2. And that's equal to your H plus concentration. All right. Now, once you have your H plus concentration, to get your pH, you do a negative log. So negative log of this, and that's where the extra acid base stuff comes in, gives you a pH of what? pH of 1.88, but they're asking for the pOH, and what do we know? We know that the pH plus the pOH equals the Kw, and we know the pKw, which is 14, and we know the pH is 1.88. So to solve for what number plus 1.8 is 14, we subtract from 14, and we get a pOH equal to 12.12, 2 sig figs, so I would go pOH is 12. Just pull it. All right, number 11. Kind of weird doing it live in front of people, but you can't see them. They're making fun of you right now. All right, so number 11, what kind of problem is this? Well, what's the pH of 0.011 molar solution of calcium hydroxide? Hint is this is a strong base. How do I know? It's a group 1 or group 2 ion with a hydroxide. So that means that every one of these calcium hydroxides dissociates into calcium plus 2 and 2 hydroxides. That's important. We've seen this before. It's called stoichiometry. So if I have a 0.011 molar solution of calcium hydroxide, that would be the actual concentration of my calcium. But because there are 2 hydroxides, wouldn't that be twice as much? Sure. Remember, this would be X. This would be 2X. We've seen this before. or B4. So of course, if this is 0.011, you would need to times that by 2. Okay, so 2 times 0.011 to be your concentration of your calcium. So obviously we do the easy math, and we get the concentration of the hydroxide to be 0.022, and that equals the concentration of my hydroxide. And now we're ready to roll. No equilibrium in this problem because we're using a strong base that completely dissociates. We've seen this before, okay? HF was a weak acid, so the antithesis, or the opposite, we had to do an equilibrium problem to do that for 10 because we didn't know how much of the 0.5 would dissociate. So this I needed equilibrium to do. Here I don't. And that's where we're kind of like mixing in the problems that we had earlier in the year. We did these types of problems. We never did equilibrium because we had problems that went completely forward, unlike the rest of these problems, especially like number 1. Number 1's a weak acid. That doesn't mean the concentration of the H plus is 0.1. It's far less than that, okay, as you can see, because it barely goes forward. So again, identifying the old questions where there wasn't any equilibrium with equilibrium is part of the skill. So in any case, I have my hydroxide concentration, and I'm looking for my pH. Well, that's pretty easy, party people. I'm going to find the pOH. That's the way that I want to do it. Certainly we can do it otherwise. So I do the negative log of the 0.022. And when I do that, okay, so when you take the hydroxide concentration of 0.022, do the negative log of that, we're going to get 1.65. And that's equal to the pOH. Now what do we know? The pKa equals the pH plus the pOH. So if I've got 1.65 plus some number equals 14, what's the pH? So I'm going to subtract 14 from 1.65, and I get my pH to equal 12.3. No equilibrium here. The idea was that all of this dissociated, and we're going to see examples of that, and that'll be clear. But we're going to deal with a lot of problems where there is no equilibrium, where we drive the reaction forward by a strong acid or a strong base in this example, or we're going to deal with places where we're going to have equilibrium by dealing with these weak acids. Hope that helped.